Hi, this is Alfawzia Nihar from At Home Tuition. Welcome to our session today. The topic that we are going to discuss in our today's video is implicit differentiation. A function can be explicit or implicit. Explicit means y equal to some function of x. When we know the x, we can calculate y directly. That is called explicit. Now let's see what is implicit. Implicit means some function of y and x equal to something else. If you look at these examples, you can understand. Explicit means y on one side of the equation which is defined in terms of x. But implicit means a combination of x and y which is equal to some number. Knowing x does not lead directly to the y. So this is called implicit type. In this form, y is expressed as a function of x. But in this form, the function is expressed in terms of both y and x. Now let us see how to do implicit differentiation. Here are the steps to be followed while doing implicit differentiation. Step 1 is to differentiate with respect to x and collect all the dy over dx on one side of the equation. And then you have to solve for dy over dx. You have to follow all these three steps to complete the implicit differentiation. Let me take few examples and explain you step by step. In our previous video, we have done quite a few derivatives, but they have all been derivatives of the functions of the form y equal to f of x. Unfortunately, not all the functions that we are going to do will fall into that form. So let's take a look at an example of a function, which is, here is an example. xy equal to 1, we are supposed to find y dash. There are actually two solution methods for this problem. This is first solution of the simple way of doing the problem. Just solve for y to get a function in the form that we are used to deal with and then differentiate. So if you solve for y, what will you get? Y equal to 1 over x. So y dash would be obviously negative 1 over x square. So that's easy enough to do. However, there are some functions for which this can't be done. You cannot rewrite the equation in terms of y. So that's where the second solution technique comes into play. Let me show you the second solution. Even in that method too, you will end up with the same solution. So in this case, we are going to leave the function in the form that we were given and work with it in that form itself. However, let's recall from the first part of this solution that if we could solve for y, then we will get y as a function of x. In other words, if we could solve for y as we could in this case but won't always be able to do. Am I right? So we get y equal to y of x. So let's rewrite the equation to note this. I'm going to just replace y as y of x. Be careful here and note that when we write y of x, we don't mean y times x. What we are noting here is that y is some probably unknown function of x. This is important to recall when doing this solution technique. The next step in this solution is to differentiate both sides with respect to x, as d by dx times we are just taking d over dx of both the sides of the equation. Actually, the right side is easy. It is just the derivative of a constant. The left side is also easy, but we have got to recognize that we have actually got a product here, the x and the y of x. So to do the derivative of the left side, we will need to do the product rule. So by doing the product rule, we will get, hope you're familiar with product rule. We have already made few videos regarding the product rule. In case if you get any query, you can refer those videos also. Now let's proceed with this. We are going to apply product rule on the left side of the equation. Keep the second function as it is, find the derivative of first function, plus sign in between, and keep the first function as it is and find the derivative of second function. That is called product rule. So the left side would become, we have applied the product rule, and on the right side it is just a constant, so the derivative would become 0. Now recall that we have the following notational way of writing the derivative. So d over dx, y of x can be written as dy over dx, which is nothing but y dash. Am I right? So you can rewrite this. Using this, we get the following. Please note that we have dropped the x on the y as it was only there to remind us that the y was a function of x. And now that we have taken the derivative, it's no longer really needed. We just wanted it in the equation to recognize the product rule when we took the derivative. So let's now recall just what were we after. we were after the derivative of y dash. Am I right? And please notice that there is now a y dash in the equation. So to get the derivative, all that we need to do is solve the equation for y dash. You have to isolate y dash on the left side of the equation and shift all the other terms to the right side of the equation. Yes, there it is. Using the second solution technique, this is our answer. This is not what we got from the first solution, however, or at least it doesn't look like the same derivative that we got from the first solution. Recall, however, that we really do know what y is in the terms of x, and if we plug that in that, we will get again the same answer. So y can be written as 1 over x. So there is a negative sign always here. If you do the fractional division, you will get negative 1 over x square, which is what we got from the first solution. Regardless of the solution technique used, we should get the same derivative as the final answer. Does this make sense to you? This is the first example. The process that we used in the second solution in this example is called implicit differentiation, and that is the topic of this video too. So in this example, we were able to just solve for y and avoid implicit differentiation. However, in the remainder of the examples in this video, we either won't be able to solve for y, or as we will see in one of the examples, the answer will not be in a form that we can deal with. Okay, now let us move on to the next example. And here in the second solution, we replace the y with y of x. Am I right? And then we did the derivative. Recall that we did this to remind us that y is in fact a function of x. We will be doing this quite a bit in the following problems, although we rarely actually write y of x. It is just for your understanding. Until you get practice, you can rewrite that. Or else, after practicing, you can just use the y as it is. So before we actually work any more implicit differentiation problems, let's do a quick set of simple derivatives that will hopefully help us with doing derivatives of functions that also contain a y of x. Here is the next question. These are written a little differently from what we were used to seeing here. So this is because we want to match up these problems with what we will be doing in this video. Also, each of this part, each of the the examples that I'm going to discuss has several functions to differentiate, starting with a specific function followed by a general function. So this again is to help us with some specific parts of the implicit differentiation process that we will be doing. Okay, let us start with the solution. So with this function here, we are being asked to do the following. You have to find the derivative of this function. So if you find the derivative, you will get. Please notice that we have a function within another function. It is an exponent function. Under the parenthesis, we have another function. So this is just the chain rule. So if you apply the power rule 5 times this function, 5 minus 1, and then you have to find the derivative of the inner function. So we will get derivative of inner function is 15x square minus 7, and the third term would turn into 0 because derivative of a constant is 0. Hope you are clear till this step. We differentiated the outside function, the exponent of 5, and then we multiplied that by the derivative of the inside function. I mean the stuff inside the parenthesis. For the second function, we are going to do basically the same thing. We are going to need the use of chain rule. The outside function is still the exponent of 5, while the inside function is this time is simply f of x here for this one. So 5 times f of x raised to 4, and the derivative of inner function is f dash of x. Here in this example, we don't actually know what f of x is, so when we do the derivative of the inside function, all we can do is write down the notation of the derivative, that is f dash of x. Here we need not go in depth. Actually, we do not know what this means, f of x. Now let's look at the final function. With the final function here, we simply replace the f in the second function with the y. Since most of our work in this video will involve y's instead of f's, outside that this function is identical to the second, so the derivative would be. That's it for this example. We found the derivative of all the 3 functions given. Now let's move on to a trigonometric problem. I mean the function, trigonometric function. We're going to find the differentiation. Here is the next example. The first function is to differentiate here is just a quick chain rule problem again. So here is its derivative. D over dx of sine 3 minus 6x would be. Derivative of sine is negative cos. Okay, this is positive cos. Cos of 3 minus 6x. And if you differentiate the inner function, you will get negative 6. So the derivative of the first function would be negative. That's it for the first function. Now let's look at the second function. For the second function, we didn't bother this time with using f of x and just jump straight to y of x for the general version. This is still just a general version of what we did for the first function. The outside function is still the sign and the inside is given by y of x. And while we don't have a formula for y of x, and so we can't actually take its derivative, we do have a notation for this derivative. Here is the derivative for this function. So in this set of examples, we were just doing some chain rule problems where the inside function was y of x instead of a specific function. So this kind of derivative shows up all the time in doing implicit differentiation. So we need to make sure that we can do them. Also note that we only did this for 3 kinds of functions, but there are many more kinds of the function that we could have used here. So it's now time to do our first problem where implicit differentiation is required. Unlike the first example where we could actually avoid implicit differentiation by solving for y. Okay, we can continue the video in the second part. In case if you have any query regarding the topics we covered in this video, you can let me know. See you in the next video.